Okay, hi everyone. My name is Alon, and I work at Outbrain. I lead the data infrastructure team. And I came here today to share with you some of my experience with upgrading large-scale Hadoop clusters. I'm not going to talk about specific versions. I'm not going to talk about specific features. I'm going to focus about what it took us to perform this massive scale migration without impacting production. Okay, so first, let me introduce you to Outbrain and our mission. So at Outbrain, we do our best to connect audiences with great content. You probably recognize us from the areas next to articles you read online. And here you can see an example from CNN. So these are the internal recommendations we provide for articles within CNN. And these are the promoted articles we provide for content outside of CNN. So we're providing 250 billion recommendations each month. And we're doing so for over 550 million monthly unique readers. We operate over 3 data centers with 6,000 physical servers. And we know a little bit about what Outbrain is doing. And now I want us to take a look at how it's done. So this is a schematic view of our logical architecture, and it will lack a bit in details, but it helps to grasp the general ideas with regards to data and how it is being used. Okay, so we have the readers, right, the users, and she's reading content online. She receives recommendations from Outbrain's services. And during this process, events are being created and pushed into Hadoop. Now, this is just one example, right? One use case in which events are being created and pushed into Hadoop. And there are actually dozens of others. And totally, we are pushing something like 80 billion events each day to provide these 250 billion recommendations a month. And once this data reaches Hadoop, the processing layer begins to take its place. So we have hundreds of flows, right, processing results, and either pushing them back into Hadoop for additional processing or into our other databases to be used by other applications. Now, some results will be pushed into our serving data stores to be used to improve future recommendations, and some results will be pushed into the data warehouses to be used by the BI teams and customer reports. Now, one thing that's very clear from looking at this diagram is that if for any reason data is missing or delayed, or processing is missing or delayed, 2 things will happen. One is that we will have stale recommendations, which will provide poor user experience. And the other is that BI and customers' reports will have missing or delayed data, right? So all these smiling faces won't be smiling that much. Now that we understand the basic dynamics of the system and like we have a basic understanding of who our users are, let's look at our physical architecture. Okay, so we have 3 data centers. 2 of them are fully fledged and very similar to each other, and they operate in an active DR environment. The third one is used mainly for serving purposes, so it doesn't have all the Hadoop ecosystem backends. Events are being created on all 3 data centers, and all events are being pushed into all Hadoop clusters. Now, there's actually a 3rd Hadoop cluster I didn't put in this diagram just to make it simpler, which is used for research purposes, right? So all events go into all Hadoop clusters. Let's talk a bit about the processing. Because we're working in an active DR architecture, most processing will take place on both Hadoop clusters. Okay, so the only example in which this is not the case is when processing results are being written to a cross-DC database, like a cross-DC shared Cassandra ring, for example. Okay, so why am I telling you all this? A while back, we decided to upgrade both our Hadoop hardware and software versions, and we had few goals in mind for this migration. First, we wanted to use new hardware that better matches Outbrain's current needs, right? As you grow in scale, your requirements will change. One example is that we wanted to increase the ratio between disks to CPU that we're using. Another important goal for us was to, like, as we grew in scale, we kept adding more and more machines to the cluster, and every time, for different reasons, it was a different hardware profile. So we ended up with a lot of different hardware profiles, which made it hard for us to just manage the resources and analyze system performance. So this was an opportunity for us to consolidate and reduce the number of hardware profiles. Now, in terms of the software versions, it was even more obvious that due to a massive growth period within the company, we've lagged behind in terms of taking advancements of newer software versions and ecosystem integrations. So, okay, we're keen on doing this project, right? And we know what we're trying to achieve. But with the growth of the company, the usage of the Hadoop clusters and the ecosystems around it grew as well. We're pushing 5 terabytes of compressed data into each Hadoop cluster daily. And the number of workflow developers, I'm not talking about developers in general, just data flows developers, is around 50, and they are spread across the world in different teams, right? They're pushing dozens of changes to how production flows behave each day. So this is a huge system, and it changes rapidly. We have 10,000 daily executions of flows, and they are working with a lot of different systems and APIs, okay, which all of these should be upgraded, right? And they are working on 300 machines, clusters of Hadoop with petabytes of data. So, okay, this wasn't going to be easy, right? And on top of that, the business constraint was clear. No user of the data platform is to be impacted during this migration. So we had to maintain the same level of service throughout this whole process. And this for us, meant 2 things. One is that we would have to manage the risk. And we would have to do it by splitting this migration process into smaller steps. And the second is that we would have to make those steps reversible so that we can maintain a stable system throughout this whole process. Okay. So we considered 3 options. The first one is to perform an in-place software upgrade. And once that's done, just do a rolling hardware update where you push new machines in and old machines out. Right? So this is the simplest approach. And you should probably have a very good reason to choose a different path if you can afford the risk. But the issue for us was that if we were going to upgrade the system in place, then we are going to expose our users to a huge amount of change in an uncontrolled manner, right? Because we have all these systems and APIs, and we are upgrading all of them in place. So this was very problematic for us. So we had to forego this option. Now, the second option is use the new hardware to install a new cluster, then sync required data, and stop processing on the old cluster and start it on the new cluster, right? So this is a little bit more elaborate process, but it's still pretty simple. Now, the problem here is that we still haven't managed the risk. We are stopping all processing on the old cluster and starting all of it on the new cluster. So we don't know if the new cluster can handle the load. We don't know if all the flows code is even compatible with the new versions of the software, right? Think about Hive queries syntax, right? It could change if you're upgrading major versions. And so, okay, we have 1,200 flows definitions, right? And we want to somehow split this task into smaller pieces. But the problem with splitting this task in this approach is that if you take just a subset of the flows, of the workload from the old cluster and start it on the new, then you will have these results for these executions missing on the old cluster. So you would have to migrate all dependencies of that initial subset. Now, very fast for us, because we have all sorts of connections between these flows, we found out that we would have to migrate most, if not all, of the flows in one swoop. So this was also problematic. Now, the third option is to start processing on the new cluster without stopping the old cluster. So this is kind of an active-active approach, because we will have like processing results on both clusters, right? New and old. And this would allow us to partition the workflow and migrate just a subset into the new cluster. And this is exactly what were our goals, right? We wanted to find this way of partitioning the load. And then if everything looks okay, so we can continue to the next partition, to the next group. Okay, so we think we have a solution here, right? But there is actually things here that we have yet to address. And first, I want us to go over our processing data layer so we can establish a common language and address those later. Okay, so we have events coming in from Outbrain services. So there are like 80 billion events a day. And these events reach Hadoop, and once they reach Hadoop, processing begins to take place using a system for orchestrating data flows that we've developed in-house, and we call the workflow engine. Now, each business group within the company has a separate workflow engine, and this workflow engine is responsible for triggering and orchestrating all the flows that are developed and owned by that business group, right? And we use this partitioning method mainly for management and scale reasons, but and during the migration, it provided us with a natural way to split the load because we have far fewer dependencies between those business groups as opposed to within each group. But this is not something that, if you use any other partitioning that makes sense in your environment, it will be just as good, right? Okay. So let's take a look at what the first step of the migration should look like. Because we want both Hadoop clusters to process the results in parallel, we want the data to reach them both. And this is fairly a simple task for us to achieve because, as you saw before, our data delivery system can publish events to multiple Hadoop clusters. So it was merely an issue of adding a new destination. Now, once the data reaches the new Hadoop cluster, then you basically have a new cluster or new hardware with a stream of the events, right? Just ready to be processed. Now, one thing to point here is that some processing types require historical data. So for these use cases, we had to do a one-time sync after the side-by-side ingestion became operational. Okay, so we are ready, right? Now that we have the data, we want to start moving processing to the new cluster. Now, one option that we rejected before was to do this, stop processing of one workflow engine, right? So the squares in the bottom here are the workflow engines of the different groups, okay? A, B, C, and D. So if we take one workflow engine, A, stop it on the new cluster, and start its execution on the new cluster, right? And that's actually problematic for two reasons. One is that if flows within A, flows that A is running, take as an input results from B, C, or D, results for these executions will not exist on the new cluster, right? Because we haven't migrated them yet. And even if you do not have cross-business group dependencies, right? Even if that's not the problem, think about what a revert process would look like. Let's say we moved A to the new cluster, and we have some sort of problem. After a few hours, can we actually revert the processing back? Well, the problem here is that if you migrate back, if you revert back after 5 or 20 hours, then you will have missing results on the old cluster, right? And because problems with data flows can take hours to be detected, then this is a real issue, right? We can't risk losing all this data. And reprocessing 20 or 40 hours of data is not a simple task in this scale. So, okay, so this is not a good idea. What we would rather have is something like this. Both workflow engines, A and A prime, are running the processing required for business group A, okay? And this way, results for this execution will reside on both Hadoop clusters. So now we can actually check that all the flows on the new cluster are running properly, that we don't have compatibility issues or load issues, right? And after these checks are done, we can continue to the next business group. And this would actually achieve our goals for gradual migration and stable process. Now, this is not as simple as it looks. And the reason is that there is an issue I've been overlooking up to this point. And the issue is that some flows should not be running twice at the same time, okay? Think about this example flow. I read data from Hadoop. I process results. I delete any pre-existing data in my target MySQL table. Let's say I want results to be in MySQL, so I delete any pre-existing data, and then I insert the results in. Now, the reason I delete any pre-existing data in this flow is for the flow to be idempotent, and so I can be able to run it more than once without impacting the results, right? Idempotency is like a basic requirement for any data flow. So if we have this type of flow, which is a basic generic flow, right? If we have this flow running twice at the same time from two workflow engines, a race condition could easily cause duplicate records because the execution order can be process, process, delete, delete, and then insert and insert again, right? So this type of processing, which is very common, we really can't have it running in the same time. Now, writing the same data sets to external databases is really problematic, and it will have many other problems, right? And it will cause data inconsistency issues. But even more than that, it will be much harder to validate the results of the migration, right? Think about it. You're looking at your target table, and something is wrong. You don't have the right data, right? Maybe data is missing, maybe data is wrong, and you're trying to understand what's the problem. But how do you know which system wrote those results? You don't, right? So the third issue, which may be like the least significant one, right, is that you double the load on your databases. You double the write load on your databases. So if your write load is significant, then doubling it would be extremely significant, right? So flows in Outbrain write to multiple types of multiple clusters of databases, external databases. We have writes to multiple clusters of MySQL, and multiple clusters of Cassandra, and multiple clusters of Vertica. So the chances for complications were extremely high, right? We had to find a way to deal with this. But how can we deal with this? Okay, so here's an idea. What if we make the workflow engine A the leader, and it will run all the flows? Now, workflow engine A prime would be the secondary, and it will run just a subset of the flows. It will run all the flows except for those that write to external databases. And that way we will have production systems unaffected whatsoever, right? While we can be testing as much of the flows as possible with real data, with real code on the new cluster. Okay, so that's much better, right? So this is much better. Now, I'm talking here about writes to external databases, but the same goes actually for any side effect in your processing that is external to Hadoop. So you should treat those exactly the same as a database write. Okay, so it will look something like this. We will have all flows running on the workflow engine A, which is one business group, right? So workflow engine A, he's the leader, and he will be running all the flows. Workflow engine A prime is the secondary, and he runs all the flows except for those that write to these databases in the middle, okay? Now, this is a significant point of time, because now we can avoid any downtime that could have been resulted from failing flows, right? So if, for instance, these flows, these 4 flows there, right here, if any of these are using a syntax that is not compatible with the new versions of the Hadoop that we have installed. If we have any, let's say you have instability in your newly installed Hive server cluster, right? You're installing new Hive server cluster. You're installing basically everything from scratch, so things can go wrong. If you have capacity issues with CPUs or memory, this is the time where you will be able to find most of these issues. right? And even more important than that, because production systems are unaffected, you will have the time to properly diagnose those issues and find proper solutions for them, instead of patching the system in a rush when production systems are burning down, right? So this is super crucial. Now, when we think everything is working properly, we can do this. And now production systems are fed results with the processing of the new cluster, right? So this is actually, we are now in production mode, okay? And the old cluster serves as a hot backup, because now the revert is extremely straightforward. Think about it. This is in phase 2, right? In phase 2, the old cluster is still running subset of the flows, right? It's still running all the flows that write to Hadoop. It's essentially filling up Hadoop with everything it needs to have in order for us to be able to migrate back and maintain a stable system. So these flows in the middle, so this is the first time you're actually running them with the new cluster during this switch to phase 2. You should probably sit together with the flows owners and validate results properly, because now we are actually impacting production. And that said, because most of the things that we've changed in the installation are the Hadoop cluster and the ecosystem around it, and we have checked those thoroughly in phase 1, you should expect less friction in this phase. Okay, so let's take a look at the whole process, right? Whole of production. We have all processing on the old cluster and none on the new, right? Just side-by-side ingestion. Now we move one group to phase 1. Since this phase is safe in terms of affecting production, if we think everything is working properly, we should actually do this. We should add more and more groups to phase 1, right? So when everything, all production flows, all business groups are running in phase 1, we are actually testing as much of the system as we can without impacting production. Now, we were able to test 70% of our flows in this configuration, right? 70%. That's 70% of the code, 70% of the load, that's 70% of the integrations with different systems and APIs. That's at least, I would suggest that's at least 70% of the problems that you would have encountered in a real-life move, okay? And you're doing so without impacting production. And you're making sure that you have the time to properly respond to those issues. And when we think everything is working properly, we can push the groups into phase 2 gradually, right? And now we are doing it, now we're actually pushing them into a safe, stable, tested environment, right? This is not guessing. We know this is going to work. And if for some reason we encountered issues with load, for example, that's the most logic thing. You are adding more load, maybe you don't have enough capacity. You can always push back. And this is a stable configuration for the system to be in, right? So you push back, you get more hardware, or you analyze why the performance is not as good as you would have expected, and then you can continue. Okay, so we have a plan, right? And we think this is going to work. But we haven't talked about how we will be able to implement this, right? So we have 1,200 flows definitions, and we want to run them in all these different configurations, right? All these. So how can we do this? Now, when we first addressed this issue of implementing this concept, we started with thinking, what would we expect from the implementation to be like? Like, what are the goals for this implementation? Okay? So the first thing, first and foremost, is that we need to allow developers to be able to continue and push changes into production, right? We want phase 1 to be an elaborate phase where we are testing and validating all the results. So we can't freeze development during all this time. The second goal for us was to minimize the amount of effort it would require from our users, the groups, the developers of the flows, to migrate to the new cluster. And we had two reasons for this, right? Basically, one is that we wanted to reduce the chances of human error by reducing the complexity of the process. And the second is that we wanted to make sure it's going as fast as it could without being dependent too much on other teams' schedules, right? Because if you are in a huge company and you're trying to push a huge change throughout this company, a wide change, you need to make sure it's going to be easy for developers to do it and monitor it while they're doing it. The third goal was, it has to do with our monitoring and alerting system and its heavy integration with the executions of the flows. Because if you think about it, while we are testing the phase one integration, right, with like hundreds of flows, we do not want the users, the owners of those flows, to get bombarded with failures about flows that are failing in the new cluster because it's not currently impacting production, right? So we are testing the new cluster installation. We want these alerts to reach us, the team that is actually building and pushing this migration project. So, okay, we want to offer a solution, and we need to understand a couple of things before that. We need to understand first where are flows coming from, right? So flows reside within a workflow repository. A workflow repository is a service, and it's owned by, it's shared actually by all of the developers, right? And it contains all the flows definitions. Now, each workflow engine, every once in a while, checks with the workflow repository to see if it has any changes in the flows it should be running, flows that belong to its group, okay? And if that's the case, it will update its flow model, and this will impact future executions of that flow. Okay, but what is a flow exactly? So a flow is essentially a definition of tasks to perform with their configuration, okay? So each flow has multiple tasks, and each task can be one of many different types. You can see one example for a Hive query task and another for a scoop ETL. Now, even though these are extremely simplified versions of the configuration, right, you can already see the problem. The target Hadoop cluster is part of that configuration. So if we want to be able to run that flow on two clusters, the user would need to duplicate its code and change the Hadoop cluster name, right? And this is the point where I remind you that we have a lot of flows, right? 1,200 flows definitions. And it's not just that, but they're changing all the time. So maintaining a duplicate code base was like really a bad idea, okay? So we chose to go to a different solution. What we did is that we gave the workflow repository the capability to change flows definitions before he's serving them to the workflow engine, okay? So it would look something like this. You should remember this slide from before. This is the slide for phase one. Workflow engine A runs all the jobs, all the flows, and workflow engine A prime runs all but those that write to external databases. Now, this time, you can see where the flows are coming from, right? So we would expect here that the workflow repository will serve all the flows to workflow engine A, but just a subset of them to workflow engine A prime. And it will do so by using a rewrite strategy, right? Some sort of mutation on the set of jobs that it's serving to the workflow engine. Okay, so these rewrite strategies. You can take a look here and see some examples of the rewrite strategies that we use in production. Now, these are, you can kind of get the idea of how strong they are, right? They are very powerful, but, and we wanted to make sure that the migration API is as simple as it could be, right? And I've talked a bit before about why it's important. So we actually decided not to expose users to this strong but fairly complex API, but give them a more straightforward approach. Users could define the state, the phase of their migration, right? Either 0 or 1 or 2. And the system will infer the set of required rewrite strategies for their workflow engines, okay? So, for example, here, the group A will define themselves to be in phase 1 of the migration. And so the workflow repository will actually run no rewrite strategies for workflow engine A because it needs to return all the flows. And he will run all of these to the workflow engine A prime. So he would filter flows with external side effects. He will change the target Hadoop cluster within the definitions of the flows, right, to the new cluster. And it will redirect emails and pager duties to our team. And basically, this allows the user to control the process of migrating, right? OK, so we've talked a bit about the migration plan, right? And we've talked about the major parts of the implementation. And now I want us to talk a bit about what we've achieved. So we'll manage to work in a gradual process. We'll manage to bound the risk at any point of time by using smaller steps. And we were able to measure the system as we were putting more and more load into it, right? And this actually allowed us to prevent from overloading the system or pushing failing flows into production. Each of these steps was reversible. And we actually used it multiple times in production to revert complete groups back from production to the old cluster. And last but not least, we were able to make this process as simple as we could for developers to allow this process to get along as fast as we could. Now, one more thing that we got out of this approach to solving the problem is that because the process was gradual and stable at any point in time, we were able to actually do almost everything we just talked about on 2 data centers, on 2 different Hadoop clusters, on 2 different Hadoop distributions, right? And push both of these new clusters to phase 1 and compare them, right? Compare them in terms of performance, in terms of their APIs, in terms of their stability over a significant period of time, right? So we are not guessing. We are not reading an article online or asking someone. We are testing both of them in production, in scale, with real data, real flows, and we are comparing it between them. And this actually allowed us to choose the one that best matches our needs. So with that, I want to thank Mipar for inviting me. I want to thank this beautiful, beautiful team for pushing so hard on this project, especially Mr. Noam Gazit at the top there. And I want to thank all of you guys for listening. Thank you.
You've got 5 minutes for questions. You showed that distribution. You wanted to share some of the comparisons that you found?
Well, I don't have anything like ready with me. There are a lot of differences to these distributions, right? Basically, the one that's stuck with me is the emphasis on stability on the Mipar platform. So that's like I think this was the most important, the one that made the most impression on me. But there are a lot of differences between the systems, right? There are differences in APIs, for example. Like the API is very similar, but depends on what you're doing. You need to understand like what actually you do with the cluster. So yeah, I think this is a very good approach. If you can't test it in small scale because your actual production scale is huge, then this is a very good way to really understand which product best suits your needs. Yeah. Yeah, they are. Because as I said, some processing should be running only on one main DC. So there's a definition of that DC, main DC, and all the flows code are using this definition, right? So I can define a flow that only runs on the main DC. And I, as a user, don't care what is the main DC right now. I just want it to be running only on the one main DC. Now, if there is an issue with Chicago, for example, then we can change that definition of main DC. We can define the main DC to be New York. And now these flows will be running in New York instead of Chicago.
So you are replicating everything.
Yeah.
What if those data
Hadoop clusters? No. That's probably, well, no, Mapar has this capability, right? But I haven't seen any other product that can do that, really. And there are other implications for that, right? Because you will have latencies in the, so yeah, it can be done, I guess, but it's not as simple as.
I just wanted to understand what is
the data delivery system you're talking about?
Yes.
So yeah, the data delivery system is basically another system that we've developed in-house. It's actually an open source. You can look it up. It's called Alethea. And it allows you to publish events to multiple destinations. So you can actually publish events to Hadoop clusters, multiple of them. So just one thing to note, we are publishing events to 5 Hadoop clusters right now, right? Because we have 3 production clusters and 2 new ones during the process. So we had to publish all events into 5 Hadoop clusters. And additionally, we are pushing events into Kafka as well. So there are a lot of different endpoints that this data delivery system can publish the events. Yeah?
In your slides, you mentioned HDFS.
We are using, the new cluster is using Mapar.
And the second question is, you mentioned about the sampling.
Yeah. Maybe later, yeah, sure. I mean, yeah, we have a lot of different use cases for Cassandra. So Cassandra is like the most configurable database on the planet, I think. So you can use it for a lot of different use cases, and some of those use cases are actually bad use cases to use Cassandra for. And yeah, we may switch some of these. Yeah. Yeah, so actually we have a lot of systems and techniques in place to do this validation. So for example, most crucial workflows have one of their last tasks to be a validation task. So you can actually validate your results versus maybe other databases, other data centers, right? So you can do all sorts of tests. Well, the migration, so there are some parts to it, right? Because building the infrastructure, the tools that would allow us to do this process took, I guess, about 2 months, maybe 1 or 2 months, something like this. And the actual process is distributed, right? So we work with the groups to allow them to push into the new cluster. And that mainly has to do with the timeline of those groups. But it's not a long process. Yeah. Okay, thank you.